So the problem right now that we're doing is on page 84 of the Modeling Dynamic Phenomena packet, and it's something like slightly different than what we've been doing, but still solving differential equations. And this is the equation that we have to solve, and then the question basically explains the steps for how to do it. So I'm not going to read it right now. I'm just going to show you the main equation at hand, which is dy over dx plus p of x times y equals q of x times y to the n power. And normally we've been working this equation a lot. This is Bernoulli's equation, which is a type of Euler's equation, which is when y to the n is just y, or it's 1, so n would equal 0 or 1. And so right now we're going to learn how to solve differential equations when y to the n is different, so it's y squared or y cubed in these cases. So first I'm going to show you how the equation given in part A fits the description that would make it equal a Bernoulli equation. And so this was our general formula right here, and then this is the equation given in part A. And as you can see, p of x is 2, q of x is 1, and then it's continuous, so both 2 and 1 are continuous, and n is a real number too. So in the problem, it says that the first step is that you start by dividing both sides of the equation by y to the n power. And so we're going to do that first. And y to the n equals y squared. We already established that. And so we're going to take each part of the equation and divide it by y squared. And then you end up getting y to the negative 2 dy over dx plus 2y to the negative 1 equals 1. And then if you were to take the equation given in the problem right here, and you were to just plug in n, then I showed right here, you would get the exact same equation either way. So you can just do it by dividing, or you could put it into the equation, but I think it's easier to just go ahead and divide, because then you don't have to remember a big formula. So the problem says the next step is to use the substitution v equals y to the 1 minus n to obtain a linear differential equation. So first we need to figure out our values for what v is equal to. And we can just plug in 2 for n and find out that it's v is equal to 1 over y, and 1 over v is equal to y. And then now we're going to have to differentiate this so we can find out what dy over dx is, because if you remember in our differential equation, as part of it is that there's a derivative in there. And so that comes out to negative v to the negative 2 dv over dx, and there is the math for that. These are the equations you have to remember going into the later part of the problem. So now we're going to actually do our substitution. And here's the original problem we ended up after we divided everything by y to the second power. And so we're substituting in 1 over v for y, negative v to the negative 2 dv over dx for dy over dx. And once we do that, we end up with this equation. And as you can see, I rearranged it a little bit right here. You can see it's a first order linear equation, just like it was promised in the problem. If you don't remember, the integrating factor, I, is equal to e to the integral of p of x times dx. We can tell from this that the p of x is equal to negative 2 because we had to rearrange it so that it would work out in the correct formula that we need. And so we know our integrating factor would end up being e to the negative 2x times e to the c. And I'm using e to the c here. You might see some different notation based on who's writing, but because we're starting off with e to the negative 2x plus c, I think it's easier just to write that for now. And then we're going to take our integrating factor and multiply it by both sides of the equation. And so here's the equation. We put it down here, multiplied it, boom. We start integrating, and we can take out an negative e to the c from both sides, because we know they're just both constants. And here it's e to the negative 2x times dv over dx minus 2e negative 2xv dx. And so we can just kind of look at this maybe from now that we've done so many of these, that we know that this is actually just the derivative of e to the 2x times v. But then just to prove it, I actually did the derivative right here. So when you derive it, you get the exact same thing, just to prove. on this side of the function that it's e to the c times e to the negative 2x times v. And then on this side of the equation, we know that e to the negative 2x's derivative is e to the negative 2x times negative 2. And so the only thing we're missing here would be the 2. So we have to do a 1/2. We have a negative, so we have 1/2 here. EC times e to the negative 2x plus k, because we're doing our integration. We don't want k's on both sides, we just want 1. And then the k is different from the e to the c. Like, they're both constants, but they both come from different times that we integrate. So you shouldn't really make them into one constant because they're two different numbers. So we still have v in this equation, and we need to take it out because we were just substituting it in. So the first thing we're going to do is divide both sides by the coefficient of v, which was EC times e to the negative 2x. And when we divide both sides, you're going to separate your variables here, and then keep your 1/2 on the bottom over here for 1/2 here. And then you're going to end up with v equals 1/2 times the quantity 1 plus k over e to the c times e to the 2x. And if that doesn't look immediately right, it's because this is times e to the negative 2, and it's on the bottom part of the fraction. So this negative is just going to be a positive. And that's equal to 1 over y. So to find what y equals, we're going to just redistribute our numbers. So you can multiply y here and then divide 2 by this quantity. And then you would get y equals 2 over 1 plus k over e to the c times e to the 2x.